Welcome to Why Math Works. Today I will present a non-traditional proof of traditional inequalities. Welcome to my channel. What if a familiar inequality could be proved without the usual algebraic routine? In this video, we will prove this and other inequalities using a surprisingly elegant comparison technique. First, let's talk about symmetry. Recall that an expression r of x and y in two variables, x and y, is called symmetric if its form does not change when x and y are interchanged. Similarly, symmetric expressions in many variables, where the number of variables n is greater than or equal to 3, are defined. We shall consider inequalities where the expressions r1 and r2 are symmetric. To use the mentioned method, we look at two pairs of real numbers, a1 and a2, and b1, b2. We say they are of the same type if the larger entry in the top pair stands above the larger entry in the bottom pair. For example, the pairs written in the green mark matrices are of the same type, whereas those marked in red are not. Now, we introduce the bracket notation. This bracket represents the sum of the vertical products. Watch how each column gives us one product, and then we simply add them together. Simple, yet powerful. This leads us to a remarkable observation that simplifies many complex proofs. Theorem 1 states, if the pairs are of the same type, then the standard bracket is always greater than or equal to the swapped version. Well, now we will prove this theorem. The difference between the left-hand side and the right-hand side of the inequality is equal to the product of the differences a1 minus a2 and b1 minus b2. This product is non-negative because the numbers a1 minus a2 and b1 minus b2 have the same sign. Thus, proof is complete. Let's apply this to a traditional inequality you likely recognize from algebra class. We want to prove that a cubed plus b cubed is greater than or equal to a squared b plus ab squared for all a and b non-negative. Since the inequality being proved is equivalent to a plus b times a minus b squared greater than or equal to 0, the solution set is represented by the shaded region in the picture, from which it is clear that, for non-negative a and b, the inequality holds. But now, let us turn to our non-traditional proof. First, we express the left side as a bracket of the pairs a, b and a squared, b squared. Next, we look at the swap bracket, which gives us the right side of our inequality. Rewrite. Since the pairs a, b and a squared, b squared are of the same type, while the pairs a, b and b squared, a squared are not of the same type, it follows that a cubed plus b cubed is greater than or equal to a squared b plus a b squared. Note that equality is possible only when a equals b. Thus, proof is complete. Next, we will apply this same idea to even more complex and beautiful inequalities. We want to prove that for every real numbers a and b, a to the fourth power plus b to the fourth power is greater than or equal to a cubed b plus a b cubed. Since the inequality here is less than or equal to b implies c cubed is less than or equal to b cubed, Theorem 1 yields the following inequality, whose left side equals to a to the fourth power plus b to the fourth power, and right side equals to a cubed b plus a b cubed. Note that equality is possible only when a equals b. Thus, proof is complete. Are you all ready for other inequalities? So, go ahead. We shall prove this inequality. Here you can see a visualization of the inequality when a equals 1 and b equals 1.5. Let us prove the inequality. If a squared is less than or equal to b squared, then a to the sixth is less than or equal to b to the sixth, and 1 over b squared is less than or equal to 1 over a squared. Thus, according to Theorem 1, the following inequality holds. The left side of inequality equals to a to the fourth plus b to the fourth, and right side equals to a to the sixth over b squared, plus b to the sixth over a squared. Note that equality is possible only when a equals b. Thus, proof is complete. Now it is time for the fourth example. We shall prove the last inequality in this video. Let us rewrite the inequality being proved. Since the left-hand side and right-hand side of the inequality highlighted in yellow can be obtained from the bracket notation, and the pairs constructed as square root of a, square root of b, and 1 over b cubed times square root of b, 1 over a cube times square root of a are of the same type, it follows that the yellow highlighted inequality holds for non-negative a and b. Note that equality is possible only when a equals b. Thus, proof is complete. That is all for today. In the next video, I will continue the presentation on non-traditional proofs of traditional inequalities. You will learn how inequalities with 3 variables can be proved in a non-traditional way. Thanks for watching. If you enjoyed this video, please give it a like, subscribe, leave a comment, and share it. Thank you, and stay tuned for another interesting video coming soon.